YouTube title options. German troops couldn't believe. The Americans could see through smoke and fog. The secret radar that made Allied guns shoot like magic. How MIT engineers built a weapon the Nazis couldn't stop when American guns started hitting targets. They couldn't see the radar. That won World War II, and you've never heard of it. YouTube description. February 1944. Anzio beachhead. German bombers attacked under cover of darkness, confident their new radar jammers would blind Allied defenses. Then something impossible happened. American guns began shooting them down with perfect accuracy, in complete darkness. The secret was the SCR-584, a revolutionary microwave radar system that could track aircraft, automatically guide anti-aircraft guns, and even follow artillery shells in flight. German troops couldn't understand how American gunners were hitting targets through smoke, fog, and darkness with uncanny precision. This is the story of how MIT's radiation laboratory created one of World War II's most important weapons, a radar system so advanced that it shot down 82% of V-1 rockets on a single day, saved countless lives at Normandy, and changed aerial warfare forever. SCR-584, WWW-2 technology, radar history, MIT Rad Lab, V-1 defense, Anzio battle, World War II, arch military history, Allied technology, secret weapons. Tags SCR-584. Radar World War II technology, MIT Radiation Laboratory, Anti-Aircraft Defense, V-1 Flying Bomb, Battle of Anzio Normandy Invasion, Proximity Fuse, M9 Director Radar History. Transcript The Impossible Shot. February 24, 1944. The Anzio beachhead in Italy. American and British forces were trapped in a narrow strip of land surrounded by German forces on three sides, with their backs to the Mediterranean. For weeks, the Luftwaffe had been pounding them relentlessly. Every night, German bombers appeared overhead, and Allied anti-aircraft batteries blazed away into the darkness, burning through thousands of shells for every plane they managed to hit. The Germans knew this. They'd recently captured an early American radar unit and developed jammers specifically designed to blind it. They were confident their aircraft could operate with near impunity. That night, everything changed. Two strange trailers had been dug into the beachhead overnight, buried up to their rooftops, with only their rotating dish antennas visible. When 12 German bombers approached the beachhead in darkness, the American gunners didn't fire blindly into the sky. They didn't use searchlights. They didn't need to see their targets at all. The four 90mm anti-aircraft guns rotated smoothly, tracking something invisible, and began firing with mechanical precision. 7 of the 12 German bombers were destroyed. The survivors fled. The Luftwaffe didn't return for a week. When a single reconnaissance plane finally appeared to test the defenses, it was shot down immediately. 10 more of these mysterious systems arrived that week. The air threat to Anzio effectively ended. German pilots couldn't understand what was happening. How were the Americans shooting them down in complete darkness? Their jammers were supposed to work. Nothing should have been able to track them. But they were being destroyed with a precision that seemed impossible. The weapon that terrified them was designated SCR-584 Signal Corps Radio, set number 584. It was a microwave radar system developed in complete secrecy by MIT's Radiation Laboratory, and it represented the most advanced fire control technology on Earth. When paired with the M9 analog computer and proximity-fused shells, it created what soldiers called the deadly triad, a weapons system so effective that enemy aircraft had virtually no chance of survival once caught in its beam. The Secret Laboratory. The story begins in September 1940, when a group of British scientists arrived in America carrying secrets. The Teazard mission, as it became known, was Britain's desperate gamble. London was burning under German bombing. The Battle of Britain raged in the skies. Britain needed American industrial might, but the Americans wouldn't commit resources without proof that the British had something valuable to offer. The British team brought blueprints, prototypes, and technical documents covering everything from jet engines to explosives. But the most important thing they carried was small enough to fit in a box. It was called a cavity magnetron. This device could generate powerful microwave radio pulses at wavelengths around 10 centimeters far shorter than anything American engineers had achieved. Short wavelengths meant tighter radar beams, which meant dramatically better accuracy. American radar systems at the time used wavelengths measured in meters. They could detect aircraft, but only roughly. You knew something was out there somewhere in a general direction. The British magnetron changed everything. With 10-centimeter waves, you could pinpoint exactly where something was, track its movement, and predict where it would be seconds later with extraordinary precision. Vannevar Bush, head of the National Defense Research Committee, immediately grasped the implications. If you could track aircraft precisely enough, you could automatically aim guns at them. In November 1940, MIT agreed to establish a new laboratory dedicated entirely to developing military applications of microwave radar. They called it the Radiation Laboratory, the Rad Lab. The name was deliberately vague, designed to make anyone who heard it think the scientists were working on nuclear physics rather than radar. From December 1940 until the war ended in 1945, over 4,000 scientists, engineers, and support staff worked at the Rad Lab, developing more than 100 different radar systems. The most important of these would be the SCR-584. The vision was ambitious: create a mobile radar system that could automatically detect aircraft, lock onto them, track their movement in 3 dimensions, and provide firing solutions to anti-aircraft guns, all without requiring the gunners to actually see their target. It would need to work in any weather, day or night, through smoke and clouds and fog. And it would need to be accurate enough that shells could hit fast-moving aircraft at ranges of several miles. The technical challenges were staggering. You needed a radar powerful enough to detect aircraft at 40 miles. You needed a scanning system that could search the entire sky. You needed automatic tracking that could follow a target once detected. You needed to calculate the target's course and speed continuously. You needed to predict where the target would be when the shell arrived, accounting for wind-air density and dozens of other variables. And you needed all of this equipment to fit into a single trailer that could be towed anywhere. Alfred Lee Loomis, running the Rad Lab, pushed for the system to be as automated as possible. The less it relied on human operators, the fewer mistakes could happen in the chaos of combat. Meanwhile, Bell Telephone Laboratories worked on developing the M9 gun director, an analog computer that would receive data from the radar and calculate firing solutions. The 2 systems would work together seamlessly, radar feeding data to computer controlling guns. Through smoke and darkness. By April 1942, the Rad Lab had a working prototype. To test the automatic tracking system, they mounted the radar outputs to a gun turret taken from a Boeing B-29 bomber, replacing the guns with a camera. On May 31st, a friend flew his small plane around the test area. The system locked onto the aircraft and tracked it automatically, the camera following the plane's every movement. The tracking was smooth and precise, far better than any human operator could achieve. The Army was impressed enough to order 256 complete systems the very next day. The production radar became the SCR-584. It stood about 12 feet tall when deployed with a 6-foot dish antenna mounted on top of a trailer. The antenna rotated continuously in search mode, scanning the sky at 4 revolutions per minute while nodding up and down to cover different altitudes. The system sent out 1707 microwave pulses, every second brief bursts of radio energy lasting less than a microsecond each. When those pulses hit an aircraft, some of the energy bounced back. The radar measured how long it took for the echo to return, calculating range with an accuracy of about 75 feet. The direction was determined by where the antenna was pointing. The result was a precise 3-dimensional position. But the revolutionary part was what happened next. Once an operator designated a target, the SCR-584 switched to automatic tracking mode. The radar used conical scanning. The beam rotated in a tight cone around the target, checking constantly whether the target was drifting out of center. If it was, motors automatically adjusted the antenna to keep the target precisely in the middle of the beam. The system could track aircraft moving as fast as 600 miles per hour. It could follow targets through clouds, smoke, fog, rain, or complete darkness. Weather that would blind optical systems meant nothing to the SCR-584. The M9 Director received continuous position data from the radar. It calculated the target's velocity and acceleration, predicted its future position, and determined the precise angle and elevation the guns needed to fire at, accounting for the flight time of the shell, the rotation of the Earth, wind speed, air density, and temperature. All of this happened automatically, continuously, dozens of times per second. The gun crews didn't aim. They just kept loading shells. The system did the rest. German troops who encountered the SCR-584 found the experience profoundly unsettling. You could use smoke screens, the guns still hit you. You could attack at night, the guns tracked you perfectly. You could fly through clouds, it made no difference. You could hear the shells exploding around your aircraft with mechanical regularity. Closing in, and there was nothing you could do except pray and try to escape the area. Some German pilots reported feeling like they were being hunted by something that could see through walls. They weren't entirely wrong. The buzz bomb killers. The first SCR-584 units shipped to North Africa in late 1943 for training. The combat debut at Anzio in February 1944 demonstrated the system's devastating effectiveness. But its finest hour came several months later, during Operation Diver, the British operation to counter Germany's V-1 flying bombs. Starting on June 13, 1944, 1 week after D-Day, Germany began launching V-1s at London from sites in occupied France. The V-1 was a small pilotless aircraft powered by a pulse jet engine that produced a distinctive buzzing sound. Londoners called them buzz bombs or doodlebugs. Each one carried nearly a ton of high explosives and flew in a straight line at over 400 miles per hour. When the engine cut out, the V-1 fell and exploded wherever it happened to be. The psychological effect was terrible. You could hear them coming, that ominous buzz growing louder. Then sudden silence. You had perhaps 10 seconds before the explosion. Nobody knew where it would hit. Fighter aircraft could shoot them down, but it was difficult. The V-1s were small, fast, and flew at low altitude. Pilots had to dive from above to match their speed. Even then, hitting such a small target was challenging. Anti-aircraft guns had even worse results. Initially, they were only destroying about 4% of the V-1s that entered their firing zones. Gunners were firing 2,500 shells for every V-1 destroyed. It was an impossible situation. Nearly 100 V-1s per day were hitting Britain at the peak of the campaign. Something had to change. In early July, British Anti-Aircraft Command made a drastic decision. They moved the bulk of their defenses, guns, radar units, equipment, and thousands of troops to the southern coast. The idea was to create a gun belt between the launch sites and London, shooting down as many V-1s as possible before they reached populated areas. The Americans released SCR-584 units that had been earmarked for the continent. More importantly, they released the proximity fuse. The proximity fuse was a miniature radar built into an artillery shell. When the shell came within a certain distance of a target, usually about 70 feet, it automatically detonated. You didn't need a direct hit anymore. Getting close was enough. The combination of SCR-584 radar M9 director and proximity fuse was devastating against the V-1s. The flying bombs flew straight and level, making them ideal targets for the system. The radar could detect them at 26 kilometers and track them automatically from that point forward. The M9 calculated the exact moment to fire. The shells detonated in proximity to the target. The results were extraordinary. In the first week after the systems were deployed to the coast, 17% of V-1s entering the gun belt were destroyed. 2 weeks later, the rate climbed to 60%. By late August, 74% of V-1s were being shot down. On one exceptional day, August 28th, 82% were destroyed. The rate of shells needed dropped from 2,500 per V-1 to just 100. With proximity fuses, it eventually dropped to 156 shells per kill, still not perfect, but compared to the alternative, it was miraculous. By September, as Allied forces advanced into France and overran the launch sites, the V-1 campaign largely ended. Of the roughly 10,000 V-1s launched at Britain, defensive measures destroyed about 7,500. The SCR-584 units had been crucial to that defense. Without them, many more thousands of civilians would have died. The war in Europe. 39 SCR-584 units landed at Normandy on D-Day, June 6, 1944. They'd been waterproofed specifically for the invasion. Their job was to protect the beaches from Luftwaffe attacks. German pilots quickly learned to avoid areas where the systems were operating. The radar-directed guns were simply too accurate. If you got caught in their tracking beam, you were probably going to die. As Allied forces pushed across France, the SCR-584 units moved with them. They operated in the rapidly changing front lines, where traditional anti-aircraft defenses would have been too slow to set up. But these were mobile systems. You could deploy them quickly, defend an area, then pack up and move forward. They shot down German aircraft with such consistency that the Luftwaffe largely stopped attempting daylight raids in areas where SCR-584s were known to be operating. The systems proved valuable in ways the developers never anticipated. Radar operators discovered they could detect German vehicles at ranges up to 26 kilometers, far beyond visual range. Suddenly, these anti-aircraft systems were providing early warning of ground movements. More remarkably, the radar could track artillery shells in flight. Shells travel in ballistic arcs, and the SCR-584 could follow them from launch to impact. Allied forces began using the radar to track enemy artillery fire, calculating backward from the shell trajectory to pinpoint the location of German gun batteries. Counter-battery fire became dramatically more effective. During the Battle of the Bulge in December 1944, terrible weather grounded Allied aircraft for days. Heavy fog blanketed the Ardennes forest, where German forces had launched their surprise offensive. Hitler had planned the attack specifically for winter, counting on weather that would neutralize Allied air superiority. For the first several days, the only tactical air support available to American ground forces was provided by SCR-584 controlled systems, guiding aircraft through the fog and clouds to their targets. The radar could see what human pilots could not, the technology that worked. The Germans had their own fire control radars. The Würzburg system was sophisticated and had introduced conical scanning before the Americans developed it. But German radar development never achieved the integration and automation that the SCR-584 demonstrated. German systems required more operators, more manual adjustments, more room for human error. The SCR-584 and M9 combination reduced the crew requirements dramatically while improving accuracy. It was easier to use, easier to train on, and more reliable in the field. Perhaps more importantly, American industry could manufacture these systems in quantity. Chrysler, Westinghouse, and General Electric produced the components. By the end of the war, approximately 1,700 SCR-584 systems had been manufactured. That was enough to deploy them wherever they were needed. Europe, the Pacific, coastal defenses. The systems weren't rare wonder weapons available only in limited numbers. They were standard equipment produced at scale, deployed widely. German forces tried to counter the systems. They developed radar jammers. The jammers worked against earlier American radars like the SCR-268, but the SCR-584 operated at different frequencies and was largely immune. They tried attacking at different altitudes using different approach angles, flying faster. Nothing worked consistently. If the SCR-584 locked onto you, your odds were poor. Pilots reported the experience of being tracked, watching shells explode closer and closer, with mechanical precision, knowing the system was calculating your position dozens of times per second, predicting where you would be adjusting continuously. Beyond the war, about 1,700 SCR-584 systems were produced during the war. After 1945, the design influenced fire control radars worldwide for decades. The automatic tracking technology pioneered by the system became standard. The Navy adapted the design for shipboard use. Modified versions controlled early missile systems, including the MGM-5 Corporal. In the 1950s, SCR-584 units were used to track early rockets, their range extended by onboard transponders. One was used to track the Corona spy satellites. Remarkably, some SCR-584 systems remained operational into the 1990s. Despite using vacuum tubes and analog computers, they were so well designed that they continued functioning 50 years after their introduction. In 1995, meteorologists adapted the MP-61 pedestal from an SCR-584 for the first Doppler-on-wheels radar system. Using that sturdy, reliable mount, researchers created the first maps of tornado wind patterns and pioneered severe weather observation techniques still used today. The scientists at MIT's Radiation Laboratory coined a phrase that became famous: "The atomic bomb ended the war, but radar won it." That might be overstating things, but not by much. While the Manhattan Project consumed vast resources and produced 2 bombs that destroyed 2 cities, the Rad Lab developed over 100 different radar systems that were deployed by the thousands. These systems detected submarines, guided bombers through clouds, located German night fighters, tracked incoming aircraft, and saved countless lives. The SCR-584 might have been the most important of them all. It gave Allied defenses near-perfect accuracy in conditions where defenders previously had been nearly helpless. It shot down aircraft that should have been untouchable. It tracked the unstoppable V-1s and destroyed them in massive numbers. It guided guns through smoke, fog, darkness, and clouds. It turned anti-aircraft fire from desperate spray and pray into precise, calculated execution. The invisible advantage. German troops who survived the war told stories about facing American forces that seemed to possess almost supernatural abilities. They described how American artillery found German batteries with uncanny speed, how aircraft appeared through fog as if guided by invisible hands, how anti-aircraft fire hit targets with impossible precision. Many of these stories involved the SCR-584, though the Germans didn't know the designation at the time. They just knew the Americans could see things they shouldn't be able to see. Hit targets they shouldn't be able to operate in conditions that should have blinded everyone equally. That was the genius of the system. It made the impossible routine. Shooting down aircraft at night, standard procedure. Guiding guns through dense smoke. No problem, hitting targets moving at 600 miles per hour. The system tracked them automatically. Operating in fog so thick you couldn't see 50 feet, the radar didn't care. For soldiers raised on the idea that weather and darkness provided concealment, encountering an enemy that could see through both was psychologically devastating. The SCR-584 represented something profound about how America fought World War II. It wasn't just about having more troops or more tanks or more aircraft. It was about having better technology produced at scale, integrated into effective systems deployed widely. The SCR-584 wasn't a rare prototype or a demonstration model. By 1945, there were over 1,700 of them scattered across multiple theaters of war, all performing the same mission with the same deadly effectiveness. The radiation laboratory closed in December 1945, its mission complete. Over 4,000 people who had worked there went back to universities, corporations, and laboratories across America, taking with them the knowledge they'd gained. Some of that knowledge was classified for decades. Some became the foundation of the electronics industry. Some led directly to developments in computing communications and detection systems that we still use today. But in 1944 and 1945, what mattered most was that German troops couldn't understand how American guns were hitting them through smoke and fog. They couldn't grasp how defenses they thought they'd blinded with jammers were still shooting them down. They didn't know about the 6-foot dish rotating on top of a trailer, sending out 1707 invisible pulses per second, calculating positions 75 feet accurate at 40 miles, tracking them automatically through anything and everything. All they knew was that the Americans could see when they shouldn't be able to see, and shoot when they shouldn't be able to shoot, and there was nowhere to hide. The SCR-584 had made darkness transparent and weather irrelevant. In doing so, it changed aerial warfare forever and saved thousands of lives on the Allied side, lives that would have been lost to aircraft and flying bombs that earlier technologies simply couldn't stop. That was the power of seeing through smoke and fog. That was what happened when scientists and engineers turned invisible waves into an invisible shield. That was how MIT's radiation laboratory helped win World War II with a weapon most people have never heard of, but which German pilots learned to fear more than almost anything else in the sky.